For decades, machine learning systems were essentially high-speed filing clerks. You fed them data, and they sorted, labeled, and recognized existing patterns. Today, artificial intelligence synthesizes new information from scratch. We have algorithms writing software code, composing original music, and generating photorealistic video. The umbrella term is generative models, algorithms that study training data to create novel samples across media types. Zooming in on text reveals large language models, or LLMs, a massive sub-branch dedicated entirely to natural language processing. When an LLM writes an essay or renders a landscape, it mimics human creativity. But underneath, they are distinct mathematical engines consuming staggering amounts of physical energy. This diagram illustrates a generative adversarial network, or GAN. It pits two separate neural networks against each other in a mathematical rivalry, a generator acting as a data forger and a discriminator acting as a detective. The generator creates synthetic data from random noise, and the discriminator evaluates it against real-world examples. If the forgery fails the evaluation, the generator adjusts its math and tries again, looping until the synthetic output is indistinguishable from reality. Another approach entirely is the diffusion model. Instead of a rivalry, this system relies on a process of continuous subtraction. It starts with pure chaotic noise, like television static. By learning to reverse a gradual noising process, the algorithm iteratively removes the static until a highly detailed, coherent image is left behind. Whether tricking a digital detective or carving clear signals out of random noise, these visual models are built to manipulate continuous data, like pixels, in a single forward pass. Language requires a completely different architecture. In 2017, researchers published the transformer architecture, which discarded the old computational method of reading text sequentially, word by word. Before a transformer can process human language, it translates it into geometry. It breaks words down into discrete units called tokens and assigns each token a numerical coordinate, known as an embedding, in a high-dimensional space. Next, the attention mechanism activates. The model analyzes an entire sequence of tokens at once, mapping the mathematical distance and contextual relationships between words, no matter how far apart they are in a sentence. From there, it relies on autoregressive generation. The model calculates the statistical probability of what the very next token should be, selects it, adds it to the sequence, and runs the entire calculation again. The model does not comprehend the meaning of the words it generates. It executes massive probabilistic equations to synthesize a highly convincing illusion of human reasoning. The complexity of that illusion relies on parameters. These are the internal, adjustable mathematical weights the network uses to make its predictions. Modern frontier models contain trillions of them. Processing trillions of parameters requires custom-built infrastructure. Tech companies rely on massive data centers packed with specialized accelerator chips, designed exclusively to handle matrix-heavy mathematics at extreme speeds. All that hardware demands immense physical resources. Training a single large language model can consume enough electricity to power a small town, while requiring millions of gallons of fresh water to keep the server racks from melting down. Because the computing costs are so astronomical, very few organizations can afford to own these models outright. Instead, developers rent access, paying a fraction of a cent for every token the model processes. The output of synthetic media might seem infinite, but it is strictly bottlenecked by the real-world economics of hardware, electricity, and water. These systems also possess strict algorithmic flaws. Visual generative models often suffer from mode collapse, where the generator finds a single output that tricks the discriminator and gets stuck reproducing that exact same image over and over. Large language models struggle with hallucinations. Because they are ultimately just predicting the next most probable token, they can generate absolute, factual falsehoods with perfect statistical confidence. To mitigate these flaws, developers are moving toward multimodal integration. This fuses the pixel manipulating engines of visual models with the reasoning and context mapping architecture of large language models. This convergence enables agentic AI. Instead of simply generating a text response or an image on command, an integrated agent can use multi-step logic to plan, adapt, and execute autonomous tasks across different digital environments. We have successfully reverse-engineered the syntax of creativity. The defining challenge of the next decade is affording the immense computational power required to grant it autonomy.